Okay, so this lesson is called limiting reactants, and it's really important. It's a process that takes a little while to get the hang of it. The problems feel really long at first, but it's definitely worth the investment of understanding what we're doing and how we're doing it, because we're going to use something called an ICE chart, and that tool we use multiple points throughout the year. So if you're struggling, keep at it, keep asking questions. I have an example problem here in black font, and then I've actually color coded the steps we're going to go through. If you want to try to match my color coding, it might make your notes make more sense later, because we're going to do a whole lot on the page for this one problem. I'm also hoping that by having these typed out, you'll be able to read them better, because you all know my handwriting isn't the best. So the concept behind limiting reactants. If you think of a chemical reaction, like the reactants yielding the products, think of that like a recipe. If we have, actually, let me make up a recipe here just for the purposes of this example. Let's say we're baking some cookies, right? And in order to bake those cookies, we need 2 eggs and 1 cup of sugar, and 3 cups of flour. And that will make us 12 cookies. Okay, obviously I made all this stuff up, but it looks like a chemical reaction. But all these ingredients turn into all these cookies. Now, if you're actually going into your kitchen to bake some cookies right now, chances are you have more than 2 eggs, more than a cup of sugar, and more than 3 cups of flour. And so if you wanted more than 12 cookies, you could just make multiple batches. But eventually, let's say you wanted to make as many cookies as you possibly could, eventually you're gonna run out of one of your ingredients. Maybe you run out of eggs first, maybe you run out of sugar, maybe you run out of flour. You're gonna run out of something. The chances that you have the exact right amount of everything to make a perfectly even number of batches of cookies, that's unlikely. You're probably gonna run out of one thing first, and that thing is your limiting reactant. Continuing with my stupid analogy for one more minute, maybe you have a dozen eggs, but you have 10 cups of sugar and 18 cups of flour. The amounts you have in your pantry and your fridge versus the amounts we need here. We need 2 eggs for every 1 cup of sugar for every 3 cups of flour. Those amounts, like we use things, we have a different amount of things and we're using them up at different rates. All of that has to be taken into account when we're trying to figure out what are we running out of first. And so that can be pretty complicated, thinking, well, how much do I have and how fast am I using it? And so that's why we're gonna go through this whole process that might feel a little tedious, but it helps us keep everything accounted for. So first of all, I look at this question: 200 milliliters of 6.8 molar HCl, hydrochloric acid, react with 60 grams of NaOH. Find, and it says all these things. The truth is, regardless of what it asks for, the first thing I want to recognize is that this is a limiting reactant problem. The way I know it's a limiting reactant problem, and this is something worth writing in your notes, like off to the side, you know it's a limiting reactant problem when you're given enough information to find the moles of 2 or more, but generally it's just 2 reactants, right? Milliliters and molarity of the HCl, I can find moles from that. That's one thing I can find moles of. Also, I can find the moles of NaOH. So because I can find moles of at least 2 things right from the start without needing a mole ratio, just from the given information, it's a limiting reactant problem. We can't just do the problem with the information about HCl. We can't just do the problem with the information about NaOH, because that's not taking into account what we're gonna run out of first, what's gonna limit us from producing more. Our first step will always be to complete and balance the reaction, because like my stupid analogy above, the coefficients tell us how quickly we're using something up. So HCl is reacting with NaOH, HCl plus the NaOH. You'll want to stop and think about what type of reaction is this? Is this a double displacement? Is it an acid carbonate? Is it a decomposition? So stop and think about that. In this case, I see an acid, but I don't see a carbonate. Really, I just see 2 compounds, so it's going to be double displacement. We end up with NaCl And HOH is what I'm going to get here. You can write it as HOH, you can write it as water, whatever you prefer. Just know that it is water. Looking around, I see one H on the left, one H on the right, besides the hydroxide, one hydroxide on the left, one hydroxide on the right, one NaCl, one A, one Na, one Na, one Cl, one Cl. We're balanced. So this one has no coefficients. I wanted to start with a simple example first. It's completed and balanced. My next step is going to be to find the moles of everything that I can. So let's see, for the HCl, I'm given 6.8 molar and 200 milliliters. In order to find moles, using molarity will work. So 6.8 molar, 200 mils, I have to turn into liters. First, it'll be 0.2. If you put the 6.8 over 1 and cross multiply, you'll get that the moles of HCl are 6.8 times 0.2, 1.36. I also can find the moles of the NaOH. That's the whole reason this is a limiting reactant problem. I can find moles of both things. For the NaOH though, in this case, I'm given grams. So grams equals moles times molecular weight is how I will find the moles. Grams of NaOH to find the moles of NaOH. So I need the molecular weight of NaOH. Na is 23 plus oxygen, which is 16, plus hydrogen, which is 1. So we get 40. Divide both sides by 40. And I get 1.5 moles of NaOH. Cool, so I have my balanced reaction. I have my moles of each. I need to scroll and give myself a little more space. My next step though is going to be plugging into an ice chart. So give me a second here. Okay, so I just paused it for a second and scrolled down, and you'll notice I rewrote this. I rewrote my reactions so that it is kind of like column headers if I were making a table, like a data table almost. I rewrote that reaction, and underneath HCl, I wrote the moles of HCl that we just found. Underneath NaOH, I wrote the moles of NaOH that we just found. And then you'll see off to the left, this is for step 3, so that's why I'm now starting in orange. We're plugging into an ice chart. So I is the first row, C is the second row, and E is the last row. Pause here if you need to get caught up on your paper, and then you'll restart. I stands for initially. You don't have to write that every time, but you should keep in mind what it means. So the question said that we had 200 mils of 6.8 molar HCl and 60 grams of NaOH. So that's initially, that's like we first show up to the kitchen, that's how much ingredients we have available to us. Then we know that these things are going to react. And as they react, as we use up these reactants, the amount that we have of them available to us changes. And we'll keep changing how much we have available because we keep turning this HCl and NaOH into something else, into the salt and the water. Eventually, though, we'll run out of something and we will end our reaction, and we'll see how much we have at the end. So I complete and balance the reaction. I found the moles that I could find of each reactant, and I plug them always into that initial row. You're always going to be given initial information. Now, from here is where it gets a little more complicated, so pause and rewatch as many times as you need to. Don't let yourself get totally lost. Let's finish filling out this initial row. We've already used all the information they give us, but we actually can infer a little more. Right when you go to bake, right at the beginning of when you go to bake cookies, right? You have your flour, your sugar, your salt. Do you have any of the cookies yet? No, right? You haven't actually done the baking. So initially, when we start a chemical reaction, we have our reactants, we have our ingredients, our HCl and our NaOH, but we don't have any of our products. We haven't yet completed the reaction. So what we can always infer is that we have 0 for each of our products. We don't have any. Okay, the next thing we have to do is figure out relative to one another how much our reactants are going to change. So if you ask yourself, the reactants, the ingredients, are we using them up or making them? Hopefully you know we're using them up. So over time, the amount that we have of them available to us is going to decrease, is going to go down. We are going to subtract from those amounts. We're going to use up what we have. Meanwhile, our products, the other side of the arrow, those are the things we're making. We start with nothing, but over time, we're going to end up adding some more. We're going to end up going from zero, from none of this stuff, to some of it. So we are, for now, for this chapter, for first semester probably, we'll always have negative signs on the left and positive signs on the right, but understanding why I think really helps rather than memorizing it, right? We're using up our reactants, decrease, negative. We're adding to our products, increase, positive. And we're always gonna put X's here. Now, the number of X's we put is based on the coefficients. So I'll show you another example probably in the next video, but HCl, NaOH, NaCl, and water, all of those have a coefficient of 1. So all of those got 1x. I didn't write the 1, but I could have. For example, if there were a 2 in this balanced reaction, I would have said minus 2x. If there were a 3, I would have said minus 3x. But we don't have any coefficients here, so all of my x's are just 1. All of that we can do just from looking at the balanced reaction we had. Now, step 4. It says, figure out which reactant will run out first. Your eggs, your sugar, your flour, what's gonna stop you? What are you gonna run out of so you can't keep going, you can't keep making cookies? Are we gonna run out of HCl first or NaOH first? In this example, if you just look at the numbers, well, something that we have 1.5 moles of versus 1.36 moles of, it might make sense to you that we're gonna run out of the HCl first. We have less of it. That's true in this case because the coefficients are 1, meaning we're using them at the same rate. For every mole of HCl we use, a mole of NaOH. So if that makes sense to you, great, but still go with me and watch this process here. What I want you to do off to the side of your paper, I don't want you to change anything we have. But for step 4, what we'll always do is take the initial moles of each reactant and divide by their own coefficient. So for HCl, we're taking 1.36, and then it has a coefficient of 1, so that's 1.36. For NaOH, we have 1.5 moles, and in the balanced reaction, it has a coefficient of 1, so that's 1.5. Okay, most of the time they're not both 1, so the numbers might actually change. That, when we take the moles we have and divide by the coefficients, that's what takes into account not only how much we have, but how quickly we're using it up. So once we've done that division, and you'll want to write this in words on your paper, once we've done that division, whichever one is smaller is the one that's going to run out first. Whichever one is smaller is the one that's going to run out first. So at the end, if we run out of HCl, at the end, how much do we have? None. If we run out of it, at the end, it's 0. So whichever one gets you a smaller number in that scratch work is the one we put a 0 for at the end. Okay, there's more to do here. It looks like those 4 steps were it, but there's a little more we have to do. One sec. Okay. So we will do more, but I think I'm actually going to have you stop here and go practice up to there so it doesn't become too much. But we can answer part A. Even though we're not done with our ice chart, we can answer part A. It said find the limiting reactant. That's which chemical, which reactant are we running out of first? We figured out we were running out of HCl first. So our answer to A, when it says find the limiting reactant, would be HCl. That's the thing we're running out of first, that at the end we know we have 0 of. Okay, so we're gonna pause here. We will come back to this exact problem and keep going in the next video, but I want you to go try up to here on another problem.